We're going to talk some more about the Graham-Schmidt process and introduce the QR decomposition. So remember last time we talked about how to go from an arbitrary basis to an orthonormal basis, and that is called the Graham-Schmidt process. And we also talked about orthogonal matrices. And remember, matrices are orthogonal if Q transpose Q is the identity, and it's the same as saying QQ transpose is the identity, and that's the same thing as saying the rows are orthonormal, or equivalently the columns are orthonormal. And we also talked about that that's equivalent to saying that it preserves lengths. And yet one more interpretation is saying that it preserves angles. Okay, before we go on to the QR decomposition, there's one other property about orthonormal bases which is important, and that's the following. Suppose you have a basis v1 through vn that says that any vector can be written as a linear combination of the vi's. And figuring out those ai's can be hard, but when you have an orthonormal basis, it's actually very easy. And that's one of the nice things about an orthonormal basis. So suppose you have an orthonormal basis q1 through qn, and you're trying to write a vector v as a linear combination of the qi's. You know that you can do that. So suppose you've done that, take qj dot both sides of this equation. Well, so on the left-hand side, you just have v dot qj, and on the right-hand side, you get the sum of all these terms involving dot products with the qj. And now the key thing is that this q1 dot qj is 0 if j is not equal to 1, because these vectors are orthonormal. And there's only one non-zero term, the one where you have j for both entries, and that number is equal to 1. And so this equation is saying aj is equal to this dot product. So there you have it. There's a very easy way to compute these coordinates. You take your given vector, dot it with qj, and that gives you the coordinate of the vector in this basis. So that's extremely useful, and we'll talk a little bit more about that later. But it says that you just need to compute all of these dot products with the v's. And there's a matrix way to think of this, which is, suppose we took these vectors, the qi's, and wrote them as row vectors. Well, taking these dot products is multiplying on the right. So if you take this matrix, which is orthogonal, and just multiply it by v, that gives you the a's. So that's an even easier way to say it. Just write down this matrix and multiply it times your vector, and that gives you these coordinates. Okay, the next thing I'm going to do is give an application of this to computing least squares. And let me have a brief digression here. Suppose Q is an n by n orthogonal matrix. That is to say, QQ transpose is equal to the identity. And if you take the determinant of both sides of this equation, you get the determinant of QQ transpose is the determinant of the identity, which is 1. And on the left-hand side, you get the determinant of Q and times the determinant of Q transpose. Well, those two things have the same determinant, so you conclude that the determinant squared is equal to 1, which is to say it's the determinant itself is plus or minus 1. And for what I'm talking about here, what's important is that it's non-zero. So that's an important fact. An orthogonal matrix is always invertible. Okay, so suppose we had an equation like this: qx is equal to b, and q was an n by n orthogonal matrix. Well, q is automatically invertible, so you can solve this exactly. Qx is equal to q inverse b. So there's not really an interesting least squares problem here. But if you take R to be a rectangular matrix, suppose you took a rectangular matrix which had orthonormal columns. So here's an example. It must have fewer columns than rows, but these two columns are orthonormal. And suppose you looked at a least squares problem like this. This could well be an interesting least squares problem. And remember, the important thing in these least squares problems is to compute this projection operator, R transpose R inverse R transpose. Sorry, I forgot the inverse on those inner parentheses. And remember, this is a projection operator. And what's it a projection on? Well, the last thing you apply is R, so it must be projecting onto the column space of R. And well, L is special. It has orthonormal columns. So what does that say? It probably says that R transpose R is the identity, or maybe it's R transpose. Which is it? Let's see. If R is written like this as a bunch of column vectors, then R transpose R is a bunch of row vectors and then a bunch of column vectors. And when you take this product, all of these rows dot with all of these columns, and since it's orthonormal, indeed you do get the identity. So R transpose R is the identity, but there's no reason for R transpose to be the identity, because you're just sort of multiplying things in the wrong order. In any event, excuse me, the point is that R transpose R is the identity. So now when we go to do this calculation, R transpose R inverse R transpose, well, this R transpose R is the identity, so the fact that I forgot the inverse doesn't matter, and what we get is R transpose. And so to solve the least squares problem, the problem Rx is equal to B, the point that you get is this projection, and it's just, this is the formula. It's R transpose B. Okay. So now let's go on and talk about the QR decomposition. So the QR decomposition is very closely related to Gram-Schmidt. So Gram-Schmidt says you take a basis and you convert it into an orthonormal basis. And if you have an orthonormal basis, Q1 through Qn, you can make an orthogonal matrix out of it, Q. And I want to illustrate what's going on here with an example. Suppose you had these two vectors. Well, the way you do Gram-Schmidt, one of the variants of it is you don't change V1, and then here's the key point, is that W2 is now V2 plus a constant times W1, and in this case the constant turns out to be 3/2. So the key point is that this new vector is obtained by adding a multiple of the first vector to the second vector. And after you've done this, you get an orthogonal basis consisting of these two vectors. And then you normalize them at the end in order to get this matrix. So I want to look at a matrix version of this. And that goes as follows. Let's take these vectors and put them in as column vectors of a matrix. So that's V1 and V2. And the first thing that I did is I added a multiple of the first column to the second column. So that's just like these row operations that we've been doing, except that it's a column operation. And remember, column operations are given by multiplying on the right. So taking this second vector and adding minus 3/2 times the first vector to it, in order to get this as the first step, well, that's the first step, and then I've written down the last step here. So let's see how we achieve this by using matrices and multiplying on the right. So here's this diagram I just had. The first step was given by multiplying by this matrix, because that's how you add minus 3/2 times the first column to the second. And then the next step was given by multiplying by this matrix. In order to normalize the first row, I multiplied by this. And similarly, in order to normalize the, column, in order to normalize the second column, I do something similar, and the conclusion is that you take this matrix and you multiply it on the right by an upper triangular matrix. And it turns out to be this. When you do this multiplication, you get an orthogonal matrix, as indicated. And this matrix here that I've used is capturing all the steps of Graham-Schmidt. And it's upper triangular, so you get this formula. And I'm going to call this thing R inverse so I can move it to the other side and say that I've written A is equal to Q times R. So that is an example of the QR decomposition. So let's summarize that. You have an arbitrary basis, V1 through Vn. You put them into the columns. You make them the columns of a matrix A. And then you multiply on the right by an upper triangular matrix. That corresponds to doing these column operations. And the result is an orthogonal matrix. And by moving this guy to the other side, you've written A is equal to Q times R. And the theorem is the following. Suppose A is an n by n non-singular matrix. Then you can write A as Q times R, where Q is orthogonal and R is upper triangular and invertible. Now, we also want to look at the non-square version of this. So suppose A wasn't an n by n matrix, but an m by n matrix. But let's assume that the columns of it are linearly independent. And that must mean that n is smaller than m. It has to have fewer columns than it does rows. And what would this decomposition be? Well, it's the same idea. R is going to be an n by n square upper triangular matrix, which is invertible. And Q is going to be orthogonal. And it's just exactly the same thing as I did before, applied to a non-square matrix. And, excuse me, I said Q is orthogonal. I misspoke. The columns of Q are orthonormal. Since it's not square, it might not be orthogonal. And in terms of the size of these matrices, it's helpful to remember this is what's going on. We started with an m by n matrix with these arbitrary columns, and we've replaced it with another matrix of the same size with orthonormal columns. And the way we did that was using this n by n upper triangular matrix on the right. Okay, so one last thing to talk about is an application of this decomposition to least squares. So suppose I had an equation like this, and it might not have an exact solution, and the approximate solution, the best least square solution, is given by this formula. X is equal to A transpose A inverse, A transpose B. And if I had the QR decomposition of A, let's do this let's calculate this this guy on the right. Well, A transpose A is R transpose Q R, and this Q transpose Q goes away, and so we get R transpose R, and so this operator that we're looking for becomes R transpose R inverse times, let's see, A transpose. Well, that's R transpose, QR transpose. And that becomes R inverse, R transpose, R transpose, Q transpose. These guys in the middle cancel, and I get R inverse Q transpose. So this matrix that I'm using to solve the problem becomes quite simple. It's R inverse Q transpose. So I conclude that X hat is R inverse Q transpose applied to B. And it might be helpful to put the R on the other side and write it this way. Rx is equal to Q transpose B. And this is an easy formula equation to solve by back substitution because R is upper triangular. So this is one way to solve this least squares problem. The cost, of course, is that you have to go through the effort of finding the QR decomposition, but there are situations in which this is a good thing to do. All right, I will see you in class.